Yes, it's recording now. Okay.
So basically, all of us know about continuous group, and when we write a quantum field theory, there is always a space-time symmetry. So in our case, it's a four-dimensional symmetry, right? Because we live in a four-dimensional world. But if you want to have a d-dimensional space-time, then you will have a space-time group as SOD minus 1, comma 1. So it's all quite basic to me. But what happens in quantum field theory is that depending on the representation of such space-time group, we can have, for example, scalar fields, fermionic fields, or a vector field, right? And we are almost all of us are familiar. I mean, what we mean by scalar field or fermion field or vector field. So scalar is something that doesn't actually transform under space-time symmetry. So you get the representation in that way. And for example, in a scalar field phi, there is no index. There is no space-time index in the phi direction, right? And that's why when you quantize the theory, you have a creation or annihilation operator which don't have any space-time index, right? Just like, for example, the first is the Klein-Gordon equation, and you can always decompose your field like in this way, and you can have a ground state, and your creation annihilation operator don't have any space-time index, and usually your Hamiltonian is written in this way. So what happens in quantum field theory is that you have a vacuum, and you can almost generate all the Hilbert space from the vacuum, just acting creation operators and stuff like that, right? So for example, in vector field, we kind of do the same thing, but what is quite nice here is that there is a gauge symmetry in A, right? So when you have a gauge symmetry like that, for example, in vector field, you have to take into account the gauge degrees of freedom, right? For example, you can do it in Lorentz gauge or Coulomb gauge or whatever you want, but ultimately what will happen is that your gauge field will have kind of like this type of configuration. But want to note that here we have a AI here, right? This has like a space-time index, right? And when we try to understand the physical degrees of freedom of these vector fields, we always try to study not the representation of the SOD, but SOD minus 2 because of the gauge degrees of freedom. Right. So do you guys have any question up to now?
No, it's okay for me.
Okay. So when you have a closed string, okay, so what we are going to do is to study the massless modes of the closed string, okay? For example, here we have the massless modes here, right? The vacuum, the particles you create from the vacuum are like the massless modes, right? Anyway, so we are going to do the same thing, but before doing that, let's just quickly try to remember what is the closed string action, right? So this thing that I have wrote here is nothing but a string action, right? So here there is like a wall volume of the string which is two-dimensional, right? Because you always have a two-dimensional string. I think I have a picture here somewhere. So this is a picture, right? So you have this sigma direction and tau direction, and this is the two-dimensional wall volume of the string where we are doing the integration. So you can have two things, right? You can have either periodic string. So what will happen here, the string will close itself, right? But you can also have an open string where you have two open boundary points. So what is happening is that both of these type of strings are actually maintaining equation like that. So this x mu are the strings, okay? And alpha and beta here, the alpha or beta here are the metric on the string. And this x mu and x nu, so what we are doing, we are thinking that the string is moving in some flat directions, in some flat space-time. Right. So now to solve it, what you can do is you know that if you have a two-dimensional space-time, you can always write your metric in this way, okay? Because of conformal symmetry, two-dimensional theory is conformal, and using that, you can always write your metric in this way. And now, using the repair parameterization symmetry, you can also set phi goes to 0. And if you do that, then you're exhausting all your gauge degrees of freedom here, okay? So this Polyakov action is quite special, okay? It has like parameterization symmetry, but we are using it to make our life simple. So once you make our life simple, the equation of motion is also quite nice, okay? It's almost like a vector field, right? This is almost like a vector field. But it's quite interesting to note that this equation of motion is not enough to understand the behavior of the string, okay? Why is that? Because of the fact we are using some special configuration of it, okay? G alpha beta, and setting phi goes to 0. We have to remember that, okay? Right. So let's compute the energy momentum tensor from here, okay? So using the action here, I take the variation and I get the energy momentum tensor, right? Now, remember that we used phi goes to 0, right? So we are also using that here. And you know, so this is your energy momentum tensor, and because we used this special form of the metric, the Einstein tensor for this G alpha beta is always 0, okay? It's always 0. So the two-dimensional metric we are reusing for this, the Einstein tensor is 0, but the energy momentum tensor is something like that. But we all know that energy momentum tensor is nothing but the Einstein tensor, right? So T alpha beta is also going to be 0, right? So because T alpha beta is 0, so you have some constraint on your string configuration, right? So then what you do is that you calculate T01 and T00 and T11, because we know that energy momentum tensor is what? Symmetric. That's why T01 will also give you what? T10, and T00 T11 is also like traceless, so it's 0. So you see that only this equation of motion is not enough to describe the string. You also have to take into account of this constraint when you solve the string, right? So so we are not going to do that because it's quite complicated and it's going to take a long time. We're just going to use the same method we did for vector field. When, you know, for vector field we sometimes use this little group representation, right, and try to understand the physical degrees of freedom. And we are going to do that here exactly the same way. Before moving into that, just 1 second, is that okay? So this is the string, right? So whenever you have a closed string, it means that there is some periodic condition in the sigma direction. And whenever you have an open string, right? So you have two endpoints. Now this open string ends somewhere, right? So you have to specify either Dirichlet or Neumann boundary condition in the end of these stuffs, right? So using either periodic condition or the Dirichlet Neumann condition, as well as this equation of motion and the constraint, you have to solve the like, how you call it, like you can second quantize it, basically the string. For example, when we did here, it was quite simple, but it's not going to be quite simple, but it's going to be almost the same thing, but we are not going to do that. So we are going to now understand the physical degrees of freedom coming from quantizing this string. And yeah, so before moving into that, do you guys have any question? Imran bhai, you have any question?
Okay for me.
Okay. Matt, I think we kind of did this course together, so I don't think you have any question at this moment, right?
Oh, I'm known to forget things, but I had to learn them again and forget them again, but it was fine.
Okay, right. Riman bhai, you have any question?
I'm not that though.
Okay. Shomitra, let me know if you have any concern or question, okay? Otherwise, there is no point talking of me.
Okay, bhai. I will let you know. You can carry on.
So, Onion bhai, so basically, what was happening in case of gauge theory, okay? What was happening is that if you use your gauge condition, you almost have this kind of like equation, right? But here it's not quite the same, because here this x basically has some other interpretation, not just like scalar field theory or gauge field theory. So these are strings basically, and there is a vacuum in string theory, and just like before, there are some creation and annihilation operator for these string theories, these strings, and whenever you act with your creation operator on the vacuum, you will have some excitation. And this what are these excitations? So we are going to understand that. What are these excitations basically? Right. So in closed string, so remember that closed string was what? It was having like a periodic condition, right? And due to that, in closed string, you have both holomorphic and anti-holomorphic generators, okay? So whenever you have a ground state of 0 of your string theory here, you can always construct the first excited state in this way, okay? So remember that if you have an action like this in string theory, basically you can start with this mu and nu to be arbitrary. It can be in d dimension, okay? But in order to have a string theory action, but with no anomaly, okay, you have to restrict your mu and nu, or your space-time dimension, to be up to d, or d equals to 10. So if you do that, then what will happen is that your action will remain anomaly free, okay? So we are going to assume from here that our strings are moving in d equals to 10. And that's why when we are going to study the little group, it's going to be SO 10 minus 2, that means SO8. So SO8 is our little group. So basically these indexes J and I, they run from 1 to 8. Okay, good. Quite simple. And in case of, so just a heads up is that we are going to study the closed string configuration, But just to let you guys know that about it, in closed string, sorry, in open string, this alpha tildes and alphas are actually related by this condition, because if you just use Neumann or Dirichlet boundary condition, you will see that these alphas are related. Okay, but not in closed string. In closed string, alphas and alpha tildes are not related to each other in any way, just because of the periodic boundary condition. And this is your first excited state in that configuration. So this is our picture, right? In closed string, you see that we have a period from 0 to sigma. Sigma has a period from 0 to pi. Sorry. Right. So for closed superstring, the first excited state is what? This. Okay. Now, so but remember that our string theory is supersymmetric, right? So these alphas, they can be bosonic or fermionic in nature, meaning these alphas can be coming from a vector representation or a fermionic representation as well. Okay. So you see that you can have these alphas, they can be bosonic or they can be fermionic, but because they have states, they have space-time indexes, they are always vector-like for the bosonic part, right? Right. So we are dealing with our SO8, right? So SO8 comes from Lie algebra classification D4, but we are not going to bother so much about it. Just to let you guys know that SO8 has 4 Cartan generators. Okay, meaning that the algebra is like has 4 Cartan generators, meaning they commute with each other. Whatever, not quite important. But so what happens is in SO8, just like in SO4, is that you can have a vector representation or a spinor representation, right? Quite simple, just like SO4 or SO3,1. Now, so what is happening is that you can have a vector representation, but they comes as a direct product state, right? So what happens is that when you have direct product state, you finally need to write them as a summation state, right? Meaning that so you see that alphas can be like vector times vector, they can be spinor times spinor, and okay, so as you know, in event dimension, okay, event dimension, you can have chiral spinors or non-chiral spinors. So I'm going to write the S's, the chiral ones as S and the non-chiral one as S tilde. Okay, right. So this is our total structure. We have to understand what is in the vector times vector state. So what is going to happen when we have vector times vector, or when we have spinor times spinor, or maybe vector times spinors as well. So what is going to happen then? So if you have a vector times vector, okay, so this is your direct product state, and you can just do some simple math. Is that vector times vector gives you something like that as well. These are the representation. These are the irefs, but in the direct somewhere. So in your quantum field theory, you will finally have these states as your irefs. Okay. So basically, what was happen is that if you have 100 times 100, what you have to do when you do the algebra, you have to take all possible linear combinations in here. Okay. But before, if you try to do this this computation, you should know that 100 means the same thing as all of them, right? So these are all vector representations. So I'm just going to take one of them here and also one in here. So if you do that, first thing what you can do is you can just do the summation and you will have a 200 state, or you know 1000 is also the same as this 0100, and you can sum them and have a state like 1100. So 1100 is same as 10110 or 1001. So I'm just going to write one of them here. And also what you can do is you can subtract one from the other, and you have a state like that. Right. So this is some 200 state, and this is 1100 state, and this 0000 state. So what are these states basically? Okay. Right. So before going to the fermion times fermion, let's try to understand them. So if you have a vector field, your representation will look like this: 1000. If you have an antisymmetric field, you will have 1100. And if you have a three form field, you will have 1110. And if you have a four form field, you will have C mu, something like that, right? So, and when you have a 2000 state, that means you have a symmetric two tensor. So you have here you have an antisymmetric two tensor, and when you have 2000, you will have a symmetric two tensor. Sorry, I forgot to write it. But so at the end, what will happen if you have V times V in your string theory? In the low energy spectrum, you will have a metric field, which is what? A tensor with symmetric two rank two tensor, and a B field, which is an anti-symmetric rank two tensor, and you will have a scalar field phi. So these are the stuffs you will have in your low dimension, in your low energy effective action. Okay. Do you guys have any question about it?
So I have a question, a very nice
Sure.
one.
Yeah.
So you are considering SO8 and its
Right.
specification. I mean, it's a representation, and then
Right.
from that representation, so you considered a specific representation, is it right, or just a generic representation?
So what I'm saying on your is that is the following. So basically, you know, you have these strings. Okay, let me just I didn't write an equation because it just makes things messy. But let me just open something real quick. Right. So I didn't actually do the mode expansion. Okay, Bhaiya? So I didn't do the mode expansion. So if you actually do the mode expansion, they are quite ugly looking. Okay. So without doing it, I'm just considering what representation this alphas come from. Okay. So if these alphas come from the vector representation, I'm getting the vector times vector. And this, if this alphas comes from the spinor representation, then I'm taking, you know, spinor times spinor.
All possible representations like vector, spinor, scalar.
Right.
all possible representation. So
it doesn't have a scalar representation because of the fact I'm telling you. Because you see, here is like a mu always.
Mhm.
But so what you should remember is that in string theory, you basically, you know, when you do supersymmetric, so here we are not showing the supersymmetric counterpart, but what happens, for example, in supersymmetry, what we do is that we have like the bosonic algebra, and also we try to write a fermionic or generators for the Lorentzian algebra as well. And here we are not doing it, but when you do actually supersymmetric theory, you will have both both fermionic generators and both vector generators as well. So when I was doing my thing, I took both of them.
okay, it's clear. Thank you.
But because it's in SO8, right, and it's even dimensional, so you should be careful that it has anomaly, right? And it also has like because it's even dimensional, it
You mean chiral?
Can have chiral or antichiral representation, you know, chiral or non-chiral, sorry, not antichiral, non-chiral, right?
Okay.
So you have to take both of them into account. Okay.
Okay, so basically you are, for spinor representation, you are actually considering Weil representation, right?
Right, yes.
Okay.
Yes,
Okay.
Yeah.
Thank you.
I think so. Because of the fact I think the strings are massless, that's why.
That's why Weil.
So
Just one complementary question. So can we
Right.
take also Majorana representation?
I mean, yeah, I don't think. Wait, I'm not sure if we can take Majorana, because Majorana fermions are chargeless, right? But these fermions are charged. These fermion generators are charged under some other field. For example,
Okay. So okay. Then
for example,
okay. Perfect.
yeah, I don't think you can take Majoranas. Right. So before continuing, okay, to fermions, fermion times fermion. Right. So I'm not going to tell you the proof because it's quite, I don't know if it's quite lengthy or not, but what happens is that these are the spinor representations, and you can have plus half or minus half, okay, of their charges. But if you have even numbers of fermions here, I'm calling those representations non-chiral representation. And if they have odd number of minus halves, then I will call them chiral representation. Okay. For example, this is non-chiral because you see plus half, plus half, plus half, plus half. There's a 4 plus halves and 0 minus half. So this is a chiral so it's a non-chiral representation. Sorry. And the next one is also non-chiral, right? This is also non-chiral because it has even numbers of minus halves and even numbers of plus halves as well. But the point is that all the chiral representations are the same basically. Okay. So when you do this algebra, what you have to make sure is that you take all possible linear combinations of the non-chiral sectors. Okay. So for example, what you can do for this one is that simply add them and you will get them. Okay. 1 1 0 0. And for this one, what you can do is you can take this minus halves to be plus half, and there is still chiral representation, and take subtraction from this one to this one, and you will get this one. And if you have this one, then you can just take this to be plus half, and you can add them and get 1 1 1 1. So if you try to do this algebra, okay, and just do this by hand, you will see that if you have chiral, non-chiral stuffs here times some non-chiral stuffs here, these are the only three possibilities. There are no other possibilities. Okay, you can check it. So just to remind you something is that we took both of the fermions to be non-chiral. Okay, right. And you can also take vector times F. Okay, so if you do that, then you have something like this and something like this. So this is the vector thing, and this is the fermion. And you can also take now direct product of them, and you now have 3 half 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 and half 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 minus half. So this is what? This is basically this famous Rarida-Schwinger operator of supergravity, and this is also some guy. I think I forgot whose super partners are they. Probably these guys, but I'm not sure. But the supersymmetric partner of G is this chi mu. Okay, sorry, I forgot to write an index here. Here should be an index. So these are quite a complicated object. These are fermions, but it has some new index as well. Right. However, this is it. This is all the stuffs you'll have in your low energy spectrum of string theory. You'll have a metric, you have a antisymmetric B field, you have a scalar phi, okay, and you have 3 form fields, one 0 form, one 2 form, and one 4 form. And you will have a fermion which is chi mu and chi. You will have 2 fermions, and that's it. That's all you will have from the non-chiral sector of your string theory. Means you're taking both S to be non-chiral. If you do that, that's it. That's what we will have in your string theory. And this string theory is called type 2B string theory. Okay, when you take fermionic generators to be non-chiral, the string theory you get is something called type 2B string theory. Right. So in conclusion, the non-chiral sector is called type 2B, and these are the stuffs you will have. Okay, you will have a 2 form, a metric, a scalar, or a 0 form, a 2 form, a 4 form, and this. So what you have to do now is take these stuffs and write a Lorentz invariant action, and you will have the low energy spectrum of supergravity. Sorry. And now you can also take your fermionic generators to be chiral. And if you do that, then the vector times vector remains the same as before. Okay, but your fermions times fermion is quite different now. Now you have chiral ones. So you are taking chiral times chiral here. Right. And if you do that, then you will have a form field which is a 3 form and a vector field here, mu. And if you have fermions times vector, you will again have a chi mu and a chi. Here the chi mu is again the Rarida-Schwinger, and chi is again the same thing we have before, a fermionic field. I just forgot the name of this fermionic field. Okay, it's also quite famous. I don't remember at this moment. Right. So in conclusion, your 10-dimensional supergravity coming from string theory can be constructed from the chiral times chiral taking both of the fermionic generators to be non-chiral, or taking the both of the fermionic generators to be chiral. And that's how you will have in both of the spectrum, you will have a metric and a B field and a phi. And here you will have also a metric and a B field and a phi. And also the fermionic sector. So these are your your fermionic terms in your supersymmetric Lagrangian, in your supergravity Lagrangian, but they are also the same. But what differs is that type 2b has forms which are even. Okay. And you know, in your type 2a sector, you will have even numbers of, sorry, odd numbers of higher form fields. Here you have a 3 form and a vector field. So that's it. That's your difference between your type 2b theory and the type 2a theory. And if you construct try to construct just supersymmetric Lagrangian in 10 dimension with n equals to 2 supersymmetry, you can see that you can only construct these two, nothing else. Okay, and this is a good confirmation that string theory could be our how you call it, quantum theory of gravity, because it can produce the correct supersymmetric Lagrangians from starting from string theory in 10 dimension. So this is more or less the basic things that I wanted to tell today, is that these are the ingredients you will have in your 10-dimensional supersymmetric supergravity Lagrangian. And do you guys have any question on it now? Hello? Yeah, Matt, tell me.
Tell you what?
Yeah, go ahead. Do you have a question?
No, you were just asking. Hello.
Okay. Anirban, do you have any question?
Okay, maybe I ask again a very naive question. So in low energy, in a supersymmetric theory, we should have all this field, right? As far as
Not supersymmetric, supergravity. You have to, if you want to include gravity, then in a supersymmetric theory, then you will have, you will see that people before string theory actually invented supergravity, right? So I was talking to Matt the other day about a lecture about GAFA. So he kind of like brings some new questions that people been pondering. Is string theory the theory, our actual theory? So basically, all started with the debate that, we are saying that this string theory is in 10 dimension, okay? So when we compactify the extra 6 dimension, are we going to get a de Sitter or a space-time with positive cosmological constant? Now you see that we have all the ingredients here, okay, in 10D. So the question is, starting from this 10-dimensional action that we're going to write with the help of this G, B, and phi and this higher form field, are we going to get a solution with in 4D which has positive cosmological constant? Now, before it, people quite long ago started pondering this question: is string theory the correct theory of theory of everything? So what Bafa was talking in that talk, maybe I can share with you guys someday. But what he was telling in the lecture is that if you have d equals to 9, let's say, okay, and you will see you will try to ask that what type of supersymmetric Lagrangian we can write there, okay, and you will see that there are not many of them, okay. There are a couple of them, and the question is that can string theory produce those supersymmetric theory starting from d equals to 10 supergravity Lagrangian, or maybe not supergravity, any string theory Lagrangian? And the answer to this question is yes. I mean, if you start writing in d equals to 9, in d equals to 8, or d equals to 7, d equals to 6, if you go down from d equals to 10, you can always write all the supersymmetric Lagrangians starting from the string theory Lagrangians. So that's a good thing, okay. But now the question is that, for example, does it have maybe a solution with a 4-dimensional solution with gravity being with a positive cosmological constant? I think that is the work that we are trying to do now. So you see that all our elements are given, and now the question is that can you have a 4D effective field theory starting from this 10D Lagrangian, and you're going to have a 4D solution with a cosmological constant being positive.
Okay, so I would also like to ask like a general question, maybe it's known to all of you except me. So say I accept this as our correct very high energy theory, this type 2A. So we know what are the particle content, this fields written, and it's in 10D with supergravity. So say we know how to compactify it in 4 dimensions.
Right.
And if that is known, and if it has been done, then in 4th dimension, in Minkowski, do we reproduce our known result in Minkowski? Like, is this A mu is same electromagnetism as we observe in Maxwell?
Well, it's some.
Or like other field, like you also have spinor field. So is this a spinor field also any of the spinor field like electron, positron, or something we have observed?
I mean, that's like I said, it's a quite difficult question to answer, because like I said to you before, that string theory comes with gravity, right? It's very hard to do the actual low energy model building starting from these gravitational forces, okay?
No, I'm asking this state of art. So has such limit has been studied or not? Of course, I understand. I'm not understand, but I take this. This is
right. So, for example, these shies, the fermions you're seeing, okay, they're supersymmetric, okay. These fermions, for example, this Rarita Shringer has a supersymmetric partner of G mu nu, and like I said, probably I'm not quite entirely sure, but the supersymmetric partner of Chi is BP, okay. Right. So now, if you want to break the supersymmetry, you have to find a suitable 6-dimensional manifold for it. So you need to, for example, say that, for example, let's say about the supersymmetric theories. Okay, whenever we were predicting some let's say n equals to 4 super Young Mills or something like that, in d equals to 4, let's say, we were compactifying the S5 compactifying the extra dimensions on a S5, okay? So when we were compactifying the S5 on S5, we were having n equals to 4 super Young Mills in 4 dimensions, right? But the problem is, you see, this we have still supersymmetry. But if you want to break the supersymmetry, you have to how I say, you have to actually specify the properties of your internal dimension, internal manifold. Okay. Now, for example, if you say that you are, let's say, compactifying your string theory on a torus, then torus has two moduli. Okay, it has a complex structure moduli and the scalar moduli, and because it has two moduli, for it you are going to have two-dimensional moduli fields. That means two-dimensional scalar fields in your external dimensions. Okay, and these moduli fields are going to set the couplings of the other fields. So if you want to actually specify the four-dimensional electrons that we see, you have to find out a manifold which is six-dimensional and breaks all the supersymmetry, but also there are finite number of them, so that you have you have how you call it, the moduli fields to be finite, and so on and so forth. And I mean, it's quite complicated to construct such moduli spaces that we see in nature, and it's constructed from the string theory. I mean, it's very hard mathematically to do, because you have to find a non-Calabi-Yau manifold, and even the Calabi-Yau is quite hard, which protect the supersymmetry. Okay, so in order to, let's say, even reproduce all the supersymmetric field theories in every dimensions, then you have to prove that there are finite number of Calabi-Yau 3 forms or 4 forms. That means finite number of Calabi-Yau 6-dimensional manifolds. Even proving that is quite difficult. Non-Calabi-Yau, I mean, I don't think people have done it explicitly, to answer your question.
Okay, no, it's very helpful. Okay, thank you.
Right. So I think we can stop the recording and talk with us, among us, maybe informally, or something else.
Okay, bye. I'm stopping the recording now.